So on Tuesday, we talked about some elementary rules for taking the derivative. There was just the one important one, and then sort of the three sort of ones that you didn't really have to commit to memory or anything, because they just sort of happened. We learned about the power rule, which was very useful. I was about to call it fun or nice, but it's useful. And we also learned about constant multiple rule, the sum and difference rules, and the derivative of a constant is zero. Those are a little less interesting. And those together lets us take the derivative of a lot of functions, but not all of them. It does do a lot. All the powers of x, including radicals and negative exponents, with x on the bottom. But not all of them. Not if they're a little more involved. But today we're going to learn about some rules that basically get the rest of the functions. All the functions we couldn't do before because we didn't know how to with the rules that we had. We're pretty much going to get them all today, by learning how to take the derivative of a product of functions or a quotient of functions. And we're also going to learn some more trigonometric derivatives. Not really something to learn necessarily. And we'll talk about taking, higher order derivatives, which sounds complicated, but it's literally just taking the derivative of a derivative, right? And you just use all the same rules, all the same process. So it's literally just doing the same thing as you've been doing, just twice in a row. All right, so first rule that we're going to learn today is called the product rule, and it's so named because it allows you to take the derivative of a product of two functions. So the sum and difference rules, right, were easy, right? If you had a sum, taking the derivative just meant you would have the sum of the individual derivatives, or the difference of the individual derivatives if you had a difference. Unfortunately, it's not so straightforward, the products. I mean, it's still relatively straightforward, but it's not, as glaringly obvious for the product rule. So the product rule is this. And you don't have to use F and G. I don't know that it necessarily tends to trip people up, but I generally like to use A and B. So if you have, say, a product of two functions A and B, and you want to take the derivative of that product, the derivative is given by the first times the derivative of the second plus the other way around, right? The second times the derivative of the first. So, in each term, right, have one function times the derivative of the other. Unfortunately, the derivative of a product is not simply the product of the derivatives. So, for an example of this, let's say we were going to take the derivative of x times x. Now, of course, that x times x is x squared, the derivative of which is 2x according to the power rule, right? The derivative of x times x is not the derivative of x times the derivative of x. It's not 1 times 1. So we can't, it's not like the sum and difference rule. You can't just take the individual derivatives, multiply them together, and then you're done. It's not that. So it's not that simple. It's exactly as simple as this appears. And no simpler than that. Yeah, that's it. And so it doesn't matter the order that you do these in, and it doesn't matter the order of the individual factors in each term. So like, if you wanted, you could switch, the order of these terms, right? You have b times a prime go first, and within each, it doesn't matter if you write a b prime like it is here, or b prime a. So like, because the operations of addition and multiplication are operations that we call commutative, right? The order does not matter in which you do them. So you can write this all sorts of ways, as long as you have each function going with the derivative of the other. Okay. So that's the product rule. You can extend this to the product of three factors, which we'll talk about later. Right now, it's it's not just you don't just take the individual derivatives and multiply them together. That's not how. So we'll use we'll do the product rule on just a product of two functions, and then we'll go up and do the product of three. And you won't often be asked to find the product of three functions. It's really not. It's really not particularly common. Okay, so here we have the product of two functions. Sure. Yeah, sure. Okay. So we have here a function that is made up of a product of two other functions. So what often helps is to sort of write off to the side what each is and what each derivative is. So here, I'm going to call this A. And I'm going to call this one B. So A is the function 3x minus 2x squared. A prime, right? So the derivative of that will be, the derivative of 3x is just 3. Minus 2x squared, the derivative of minus 2x squared, well, according to the power rule, take this 2, throw it in front. The minus 2 is already there, so throwing an extra 2 will give us a minus 4. So minus 4x, subtract 1 from the power, so just minus 4x. So the derivative of A is 3 minus 4x, right? And both of those terms are just from the power rule. For B is 5 plus 4x, and so the derivative of that, B prime, is, well, the derivative of 5 is nothing, and the derivative of 4x is just 4. So derivative is just 4. So, keeping in mind, of course, that the derivative of, I'm just going to write down the product rule here. The derivative of a product is A times the derivative of B plus B times the derivative of A. Alternatively, if you've written them down in this way, you can just, they're just sort of connected in this way, right? Just each one with the derivative of the other. So if we wanted to find h prime of x, right, the derivative of this h, that would be the derivative of, that would be a, so the original function of one. The original function of one of them, so 3x minus 2x squared times the derivative of the other, which is 4, plus the original function of the other, b, 5, so that's 5 plus 4x, times the derivative of the first, so times a prime, which is 3 minus 4x. Okay, so that's the derivative. And if you so desire, you can expand this and combine like terms and simplify it. In fact, I would recommend doing so, just because this is, this as it is kind of an eyesore to look at. So distributing that 4 into this binomial, that would be 12x minus 8x squared. And multiplying these two binomials together, right, so using FOIL, first, outside, inside, last, that would give us 15 minus 20x plus 12x minus 16x squared. Okay, so everything written out. And then I'm just going to grab whatever my like terms are and combine them. So I see 2 x squared terms. Those can be combined. And I see a couple of x terms also. Make sure you grab the sign that's in front of them as well. Like for that minus sign, with the minus 20x. So combined, that should be, and I'm just going to write my x squared terms first. Minus 8x squared minus 16x squared, so minus 24x squared. With the x terms, 12 minus 20, that's 24 and minus 20, so 4, positive 4x. And then plus 15. Right, that didn't have anything to combine it with. So that is your derivative. That is your derivative according to the product rule. That is the derivative of h. Yeah, right. It's so notice that is not just the two derivatives multiplied together, like the two individual derivatives multiplied together. So for this one in particular, because it's a product of two polynomials, we could have found this a different way. Not that we should have, right? We should be using the product rule, but in case you wanted to verify that this actually is the derivative, and that the product rule actually does work and it makes sense, we could have taken this and so you don't have to write this down because this isn't what you should be doing. But we could have taken this and actually multiplied it out, like expanded it until it was no longer a product, but rather a collection of terms. So h of x, if you multiply this out, and I'm not going to show every step, is going to be 15x plus 12x squared minus 10x squared minus 8x cubed. Which if we just combine these, we get that. And if we take the derivative of this, of this looking thing, we get 15 plus 4x minus 24x squared. Which, we can reorder those terms, 24x squared plus 4x plus 15, which is exactly the same result that we got when using the product rule. So,
what do we do?
Just for me to show you that what you got from the product rule is actually the derivative. Yeah. You probably don't want to be doing things this way. You can't always do it anyways either, because sometimes, they're not both polynomials. Sometimes one function is a polynomial and the other one is like trigonometric or something, and so that won't be. Okay, but anyways, that's the product rule, right? You put together your terms. Each term is the derivative of one with the original function of the other. Each one of these things appears exactly once. And there's a plus sign in between, and it really doesn't matter the order in which you do things as long as you match each function with the other's derivative. Okay, so this can be extended to more, the product of more than two functions, right? So here we did two functions. You can totally extend this to product of three functions or 4 or 5 functions. I don't think I've ever seen that, but you could. And the way to do that is here. So this is an extension of the product rule to the product of three functions, f, g, and h. And this looks similar to the two-factor product rule. It's just that there are three terms now, and in each term, one of the factors is a derivative, and the other factors are just the originals of the other functions. So you take, essentially, the derivatives one at a time, putting a different derivative into each term, and having the originals of the others. So, in the first term, you have f and g and h, except f is the derivative. In the middle term, you have f and g and h, except g gets to be the derivative this time. And in the last term, you have f and g and h, and this time h gets to be the derivative, and the other ones, are just the original functions. So, from this, you can sort of imagine what it would be like if you were multiplying 4 functions. There'd be 4 terms, and in each one, a different one would be derivative every time. The other 3 would just be normal. So you can extend this forever if you wanted to. Yeah, we don't have to actually do this example. We'll see some other examples later. We probably want to stick to working out two-factor, the derivatives of two-factor products for now. Okay. So, right, that's the product rule. Well, this is the product rule, right? You just take one function times the derivative of the other, plus do the same but the other way around. And that'll be the derivative of the product. And so that takes care of products. And now we know about products, and we know about sums and differences for Tuesday. The only other basic arithmetic operation to learn about is division. So we're going to learn the quotient rule. And I regret to say that it is not quite as easy to remember as the product rule might be. It does involve some things that the order of things does begin to matter. It does have to be written a particular way. And that's just due to the fact that, part of it is due to the fact that division, right? Finding quotients. Division is not one of those things that's commutative. 10 divided by 2 is not the same as 2 divided by 10, right? So the order of things does matter, and so the order of things in the quotient rule matters as well. So the quotient rule is written this way, and just like the product rule, you can write it with A's and B's, doesn't matter. And in fact, I am gonna do so. So the derivative of A divided by B, right, that quotient, is given by B times the derivative of A minus A times the derivative of B. Actually, I'm going to write it this way. The derivative of A times B minus A times the derivative of B, yeah. All over B squared. Okay, so a couple things here. This is a minus sign in between them. Don't get it confused with the product rule, which has a plus sign. And it's because of this minus sign that's in here, in the quotient rule, that the order of the things on top matters, right? Just like division, subtraction is also not commutative. 5 minus 2 is not the same as 2 minus 5. So the order does matter. And the term that is first up there has to be first. If you switch the order for some reason, what you'll end up getting is the negative of the correct derivative. If you switch the order of these, then that basically it's just sort of like you smushed in a negative sign that wasn't supposed to be there. So you'll just get the negative of the correct derivative. If you swap the bottom with A, that would do nothing. Like if you made it over A squared, it wouldn't do anything. It wouldn't be anything meaningful. It's over B squared for a reason. I wish I knew where this quotient rule came from. But it's just such a basic one, I can't imagine, it's so fundamental that I can't imagine breaking it down into smaller parts and deriving it from somewhere else. Although, right. Yeah, hold on, let me think about something. So what's the derivative of 1 over B? So A times B to the negative 1. Okay. So if this is a product, then of course I have A, I have B to the negative 1. The derivative of A is just A prime. The derivative of B to the negative 1 is negative B to the negative 2, but also times B prime, because that's a chain rule which we'll learn about later. So negative B prime over B squared. It kind of seems like I can't derive this without using something that we have yet to learn. But yeah, so this blah blah blah, A prime over B. So if I wanted to match these up, I would have A prime B minus A B prime over B squared. Okay. Anyways, so it could be derived, but it uses something called the chain rule, which we have not learned yet. So this is the quotient rule. If you're having trouble remembering the order of these two terms, which one goes first, just think of it as maybe taking the derivative from the top down, so that you take the derivative of a first. So the derivative of a is the term that appears first. The derivative and the derivative of b is in the second term. That's about as helpful. Like, I'm sure there are other mnemonics out there, but that's it is what it is. So derivative of a times b minus a times the derivative of b all over b squared. Okay. Let me just copy this for later. Okay. So we have this quotient, and we want to take the derivative of it. Just like with the product rule, it also helps to label what a and b are, and to write them off to the side. So a is the function 5x minus 2. Its derivative, a prime, will just be 5, right? Derivative of 5x is 5, and the derivative of minus 2 is nothing. B, the bottom, is x squared plus 1, the derivative of which, b prime, is 2x, right? The derivative of x squared is 2x by the power rule, and the derivative of plus 1 is nothing. So those are a prime, b, and b prime. And having written these off to the side, it makes it a lot easier to construct, the derivative, of a quotient, without having to just imagine that you didn't do any of this and you just started writing what's a? It's 5. Imagine that you were trying to figure out the derivative of things on the fly as you were writing this big fraction. So you don't really want to be doing that. So So I would recommend definitely writing off the individual pieces to the side somewhere when you have to use the product rule or the quotient rule. Okay. So first comes the derivative of a, which is 5. Times the original function of b, which is x squared plus 1. Okay, minus the original of a, which is the function 5x minus 2, times the derivative of b, which is 2x, all over the original function b squared. So the original function b being x squared plus 1. Okay, so you could totally leave it like that if you wanted. That is the derivative. Yeah, I mean, there's nothing really super amazing about this. But at least with the top, it would make it look a lot nicer probably if you were to expand it and combine like terms. I would not recommend expanding the bottom of these quotient rule derivatives, because oftentimes what's going to happen is, it's not going to happen here, but when you're lucky, what will happen is that there will be, out of nowhere, something like x squared plus 1 will appear on the top, and you'll be able to cancel it nice, and it won't be as obvious if you've gone ahead and expanded the bottom to say, x to the 4th plus 2x squared plus 1, right? So just for the bottom, just keep it looking like that is certainly what I would recommend. So 5 times x squared plus 1, that's 5x squared plus 5 minus, and I'm going to put this in parentheses because I'm not going to incorporate the minus just yet because that is confusing to me to try to do a minus and incorporate 2x at the same time. It's just minus 10x squared minus 4x, like minus all of that. X squared plus 1, all squared. Okay. So that's 5x squared plus 5 minus 10x squared plus 4x. All over the same denominator. And if I were to just combine these like terms on top, that would give me, well, 5x squared minus 10x squared is negative 5x squared. And I'm going to write these in descending power, in order of descending powers, plus 4x plus 5. And that's not factorable. At least I can't find two factors of, negative 25 that add up to 4. So that's, nothing canceled out. That's what your derivative is. That's the derivative of the original function, y. That's right here. This gives the slope at any value of x for this function. It's called for 11:45, so it's been an hour. And what's that at 11:40? Yeah.
It's probably hours.
Yeah, it's an hour and 55 minutes. It's 2 hours minus 5 minutes.
Why did you calculate this
I don't know. Because I expect to eventually just be able to remember, like, oh yeah, this class ends at this time. And yet it never happens. So that's the quotient rule. That's about all to say. That's about all there is to say about the quotient rule. So go ahead and come back in 10 minutes. Come back at 1 o'clock. So we'll call A, let me do this in a darker blue. We'll call A sine of x, the derivative of which is cosine of x. And we'll call B, or we'll call cosine of x, we'll call that B, the derivative of which will be negative sine of x. Now the quotient rule states the derivative of A over B is, right, we go sort of top down, we take the derivative of A first. So A, the derivative of A times regular B minus A times the derivative of B, right, just the other way around. All over B squared. Well, let's put that together. That is and that is derivative of A is cosine x. I definitely should have left more space. Okay. So the derivative of A is cosine of x times B, which is also cosine of x, minus a, like regular a, which is just sine of x, times the derivative of b, which is negative sine of x. All over the original b squared. So cosine of x squared. Okay, simplifying this a bit. Cosine times cosine, that's just cosine squared. And minus a negative is going to be a plus, sine times sine. And so, you know, you don't actually have to pay attention to this, but like you don't have to write this down or remember this. But, you know, this is where it would come from. Over cosine squared of x. Which, I mean, there are a couple ways you could think about this. You could split it up if you wanted to, but the easiest thing to do is probably to say cosine squared plus sine squared, that's 1. From that Pythagorean identity that we have. And so we end up with 1 over cosine squared of x. And if you remember, cosine and secant are reciprocals of one another. So if we have a cosine on the bottom, we would have a secant on the top. Now what we have is cosine squared on the bottom, so that would mean a secant squared on the top. And so we end up with that, you know, so we end up that the derivative of tangent is secant squared. You know, from the basic derivatives of sine and cosine and the quotient rule, like, you know, put together. The derivative of secant happens the same way, but even easier, because you know, secant is actually just, you know, it's not even two functions put together, it's it's 1 over cosine, which we can also find using the quotient rule. You know, if we call this, if again we call this A, and we call the bottom B, A is 1, the derivative of which is 0, so A prime is 0. And again, B is cosine, the derivative of which is negative sine. Yeah, so you don't have to remember this specifically, but it's good practice for, you know, using the quotient rule, and it's, you know, it's fun and interesting.
Where do you know the cosine for x plus sine squared x?
Mm-hmm.
How do you know what?
That's just an identity. You know, it's just a mathematical truth that if you have sine squared plus cosine squared of the same angles, that's 1. Yeah. And that's called one of the Pythagorean identities. Or, you know, it's often referred to as the Pythagorean identity, but, you know, there are others. Okay, so putting these together in the exact same way using the quotient rule, we get the derivative of A, which is 0, times B, which is cosine, minus the original function A, which is just 1, times the derivative of B, which is negative sine of x, all over the bottom function, you know, the bottom squared, so just the original function B squared. And so if you simplify this, obviously the first term is nothing because it's getting multiplied by 0. Negative times a negative is positive, 1 times sine of x, so it's just sine of x on the top, over cosine squared of x on the bottom. And there are a couple of ways to break this up, like you could, you know, bring up a secant squared, you know, sine times secant squared or whatever, but the easiest way or the best way is probably just to write it as 1 over cosine, just to split up those cosines on the bottom, 1 over cosine times sine over cosine. And so 1 over cosine is secant, sine over cosine is tangent. And so we get that the derivative of secant is secant tangent. And the derivative of tangent is, secant squared. So that's where those come from, right? And the ones for cotangent and cosecant, those happen in a similar way. It's just because the positions of sine and cosine are reversed for those, you end up with slightly different derivatives. But they have those happen in a parallel way to these if you wanted to do them for fun. But anyways, so those are the derivatives of the other four trigonometric functions. So far we have all these trigonometric functions. We have that the derivative of sine is cosine. We have that the derivative of cosine is negative sine. And now we just learned derivative of tangent is secant squared. If you just wanted to see a list of all of them, the derivative of cotangent, well, let's do secant first. Right, these are the two next most important ones. That's secant tangent. Then the two that matter a little less, cotangent. That's just sort of the flipped version of this. There's a negative sign, and instead of secant, it's cosecant. And then last, the derivative of cosecant is just sort of the flipped version of this. There is a negative sign, and instead of secant, it's cosecant. Instead of tangent, it's cotangent. So that's just all the trigonometric derivatives together. Not exactly. So we still haven't talked. So we talked about a lot of different kinds of functions, but we haven't talked about the derivatives of composite functions, right? Functions of other functions. So, like, if you were to take the derivative of a tangent that is also, subsequently being squared, or the tangent of 3x to the fourth, we don't know what that is yet. And that's coming up eventually in something called the chain rule, where we're going to sort of chain things together. And it's going to be all about, like, the fact of, composing functions inside of one another. So that question will be answered in due time. Okay. Oh, pressing that button. Okay. So let's find some trigonometric derivatives. Okay, so here y is the function x minus tangent of x. Simply taking the derivative of each of those terms, y prime, okay. The derivative of x will just be 1, as we learned on Tuesday. And there's a minus sign. And the derivative of tangent, as we learned 30 seconds ago, is secant squared of x. So that's good enough, but if you wanted to, you could write this also as negative tangent squared of x. And that fact just comes from that secant squared minus 1 is tangent squared of x. So if you were to say, take each of these, multiply by -1 on both sides, this isn't something that I would expect you to remember is a possibility. Yeah, how many are there? So many, but very few that you will actually have to remember. The reciprocal identities between like all the different trigonometric functions, like, sine is a reciprocal of cosecant, those are important. Maybe that first Pythagorean identity is important with the sine squared and the cosine squared. And then, those are the ones that are important to hold like in your head. There are a lot of other ones that matter less. Like, you'll probably just, it's probably more important that you just remember they exist, and then you'll be able to look them up at the time that you need to use them, if you ever do need to use them. Yeah. Anyways, that's +1 equals negative tangent squared of x. And, you just switch the order of these terms. If you were curious about where that came from, so you wouldn't have to write it as negative tangent squared, but you could. I just wanted to let you know that you could. But that's the derivative. Now, b is actually a product of two functions, so we would have to use the product rule. First function in this product is x. We'll call that a. The second function in this product is secant of x, and we would call that b. Right? There's no way to take the derivative of this other than to think of it as a product and to use the product rule. So the product rule is that the derivative of a times b is a times b prime plus b times a prime. Again, with the product rule, it really doesn't matter which order you write the terms in and which order you write the factors within each term, because multiplication and addition are commutative, as long as you have each one with the derivative of the other. So, of course, you can skip straight ahead to writing this, but if you wanted to write it, write the individual components somewhere off to the side, that's good too. A is x. A is x. So a prime is 1. B is secant of x, which means that b prime is secant tangent. Or tangent secant, whichever one you want to say. Secant tangent, I think, sounds a little better. So, putting these together, we'll have a times b prime. Oh, right, so, when you do this, you can always just do that to help you remember. A is, so, let me start this off with y prime equals, okay, so that A is x times b prime, which is secant x tangent x, plus b, which is, the original b, which is just secant x, times a prime, which is 1. So that would literally just be x secant x tangent x plus secant x. And if you wanted, you could, nothing I forgot, right? Like, the secant x, secant tangent, yeah, that sounds about right. If you wanted, you could factor out a secant x, yeah. And what you'd have left is x times the tangent of x plus 1. I don't know. Just, if I have a lot of, I just felt like x times tangent of x was a little bit bulky, and then whenever I factor out something and the stuff that's left inside looks particularly bulky, I sort of default to brackets instead of parentheses, but parentheses would work equally as well. Okay, so just those are they can be incorporated into the other rules that you already know of. Okay, so these aren't actual problems; these are just examples of derivatives, right? These are examples of derivatives that come about from the product rule or the quotient rule. This is product. This is product. These three are quotient. You can tell because on these three you got something on the bottom being squared. That's sort of a mark of the quotient rule. But it's just there to show you. We're not actually going to go through any of these. They're just to show you that immediately after differentiation, they can look kind of ugly. And so if you expand them, combine like terms, you can get them to look a little better. We actually did see this one. Negative 24x squared plus 4x plus 15. That was one of the first couple ones. And I think we might have seen this one as well, actually. Yeah. Yeah. But, you can often make a derivative look a lot nicer if you are willing to go the extra step of expanding and combining like terms with each other. Or, in the case of this, using identities, using some small amount of identities to clean up some trigonometric expressions. Okay. Now, we're just going to talk about some higher order derivatives. Except there's nothing new here, right? There's nothing new, really, to talk about, except for, I guess, the knowledge that you can take the derivative multiple times in a row, or that you can take the derivative of a derivative. It's not like you didn't think that could happen. It's not like you consider that an impossibility. So it's not like I'm really learning you anything here. But you can take the derivative of a derivative, and you get something called the second derivative. If you took the derivative again of that, you would get something called the third derivative, and so on and so forth. So taking higher order derivatives like this is not simply some sort of intellectual exercise, right? Sometimes, in certain cases, they actually have like a real world meaning. So, in the case of motion, right, we can start off with a position function, and we sort of learned on Tuesday that if you take the derivative of position, if you take the derivative of position, what you're doing is you're finding out how fast your position is changing. That is your speed or your velocity. So the derivative of position is velocity, right? And that's denoted by the fact that v is equal to s prime. Now, so you can also measure how fast your velocity is changing. So if you're in your car, you can start at 0 miles per hour, and you can go to 60 miles per hour. Now you have there's a possibility of doing that over 60 seconds, right? Going from 0 to 60 in 60 seconds, that's nothing. That's like, that's a pretty steady increase. You can also do it in 10 seconds, which will feel a little different, right? Going from 0 to 60 in 10 seconds. Still very comfortable. But you could also imagine going from 0 miles per hour to 60 miles per hour in the space of 1 second. And that would feel very different, right? And so there needs to be a way to describe how fast your velocity is changing. Literally how fast your position is changing. Not that you have to think of it in those nested terms. But that's what acceleration is, right? That's what acceleration is measuring. How fast your own velocity is increasing or decreasing. And so what that is if you take the derivative of velocity, you get the rate of change for your velocity, right? So you get v prime. And that is what your acceleration is. And it also happens to be the second derivative of position, right? Because velocity was already your first derivative of your position. Taking the derivative again gives you your second derivative for your position. So not only is acceleration the first derivative of velocity, it is also the second derivative of position. That means if you start off with a position function, you can derive once to get the velocity function, and you can derive again to get the acceleration function. Higher order, right, so these are known as higher order derivatives. Anything past the first derivative is known as a higher order derivative. And so if you have the second derivative and you take the derivative again, that would be the third. Take the derivative again, that's the fourth. And here's some ways that that's denoted usually. So let me just cross out these because you'll see these a lot less. So much less. Of course you see dy dx, but still, I mean, you know what that means. So if I were being proper, I guess I would say you definitely don't see any. You might see these sometimes, but very, very rarely, and often not until like calculus 2 or something. So I'm just gonna cross those out slightly lighter. So we're familiar with dy dx notation and d dx notation. But for these prime notations, so what happens is that, like, for the first three derivatives, for the first, second, and third derivative, you just denote it by increasing the number of little tick marks, right, all the way up to 3 tick marks. And past that, right, if we're going to take the fourth derivative, the fifth derivative, or whatever, it would become, like, prohibitively difficult to understand and to read that many little prime marks. So what happens instead is that the fourth derivative is denoted by a little 4 in parentheses in the corner. Whether you are using y or f. Right, and so the fifth derivative, or let's say the 17th derivative, which you will never have to find ever in your life, would be denoted by like y with a little 17 in parentheses, or f with the 17 in parentheses of x. Yeah, I mean, by the time you get to the fourth derivative, most functions either just break down into 0, or they get they either break down into 0 completely, so really simple, or they become so complicated that it just becomes not useful to talk about them. Okay, so we'll just do this in the last 3 minutes. I mean, we really can. So this is the position function for an object falling on the moon, say. And we want to know, like, what is the ratio of Earth's gravitational force to the moon's? Well, to do that, we would first have to find out what the gravitational force on the moon is. And we can do that by taking the derivative a couple times. So S of t is negative 0.81 t squared plus 2. If we took the derivative of that once, we would get our velocity function. And taking the derivative of that once, it's just the power rule. We take this, put it in front, and subtract 1, right? And that would leave us with negative 1.61. negative 1.62 t plus nothing, because the derivative of 2 is nothing. And so if we were to take the derivative of that again, we would be taking the second derivative of position, or the first derivative of velocity, and what we would get is the acceleration. And that, taking the derivative of this now, is just negative 1.62. So the acceleration, right, due to gravity on the moon is, negative 1.62, 1.62 downward. And this is in meters per second squared. Okay. So all we would have to do to answer this question then is take the ratio of Earth's gravitational force to the moon's, which means Earth's gravitational force is on top, the moon's gravitational force is on the bottom. If we're talking about meters, right, we're in the metric system, which means that we're going to use negative 9.81. So we're going to put that on top, that's Earth's, and this one that we just found, the moon's, is negative 1.62, which that's already there, is 6.06, let's say. So the ratio, right, that we're looking for is 6.06. So that's the answer to this question, although the important part, of course, is having taken the derivative twice to get, having taken the derivative of the position twice in a row in order to get the acceleration.